When the input is a file, a sequence of bytes, the first processing step is to usually parse it into a sequence of records. In a stream processing context, a record is more commonly known as event. But it is essentially the same thing, a small, self-contained, immutable object containing the details of something that happened at some point in time. An event usually contains a timestamp indicating when it happened according to a time of day clock. For example, the thing that happened might be an action that a user took, such as viewing a web page or making purchase. It might also originate from a machine such as periodic measurements from temperature sensor, a CPU utilized and metric. In the example of batch processing with Unix tools and place, each line of the web server log is an event. Uh, an event may be encoded in text strings or JSON or perhaps in some binary form, as discussed in that. The encoding allows you to store an event, for example, by appending it to a file, inserting it to a relational database, or writing it to a document database. It also allows you to send the event over the network to another node in order to process it. In batch processing, a file is written once and then potentially read by multiple jobs. Analogously, in streaming terminology, an event is generated once by a producer, also known as publisher or sender, and then potentially processed by multiple consumers, subscribers, or recipients. In a file system, a file name identifies a set of related in a file system, a file name identifies a set of related records. In a streaming system, related events are usually grouped together into a topic or a stream. In principle, a file or a database is sufficient to connect producers and consumers. A producer writes every event that it generates to the data store, and each consumer periodically polls the data store to check for events which have appeared since its last ran. This is essentially what a batch process does when it processes a day's worth of data at the end of the day. However, when moving toward continuous processing with low delays, polling, polling becomes expensive if data store is not designed for this kind of use. The more often you poll, the lower the percentage of requests that return new event, thus higher the overall become. Instead, it is better for consumers to be notified when new events appear. Databases have traditionally not supported this kind of notification mechanism very well. Relational database commonly have triggers which can react to a change. Example of being inserted to a table, but they are very limited in what they can do and have been somewhat often after the alternate database design. Instead, specialized tools have been developed for the purpose of delivering event notifications. Basically, like some messaging systems. A common approach for notifying consumers about the new event is messaging system. A producer sends a message containing an event, which is then pushed. Which is then pushed to consumers. We touched on this system previously in message messaging, but we'll go into it. The direct communication channel like a Unix pipe or a TCP connection between producer and consumer would be a simple way of implementing a messaging system. However, most messaging systems expand on the basic model. In particular, Unix pipes and TCP connect exactly one sender with one recipient, whereas a messaging system allows multiple producer nodes to send messages to the same topic and allows multiple consumer nodes to receive messages in the same topic. Within this publish subscribe model, different systems take a wide range of approaches. Within this publish subscribe model, different systems take a wide range of approaches and there is no right answer for all purposes. To differentiate the system, it is particularly helpful to ask the following two questions. Within this public subscribe model, different systems take a wide range of approaches and there is no one right answer for all purposes. To differentiate the system, it is particularly helpful to ask the following two questions. What happens if the producer and message send messages faster than the consumers can process them? Broadly speaking, there are three options. The system can drop messages, buffer messages into a queue, or apply back pressure, also known as flow control. That is blocking the producer from sending more messages. Okay. For example, Unix pipes and TCP use back pressure. They have a small fixed size buffer, and if it fills up, then the sender is blocked until the recipient takes data out of the buffer. If messages are buffered in a queue, it is important to understand what happens as the queue grows. Does the system crash if the queue no longer fits the memory, or does it write message to disk? If so, how does the disk access the performance of the messaging system? What happens if a node crash or temporarily go offline? Are there any messages lost? As with database, durability may require some combination of writing to disk and replication, which has its cost. It can afford sometimes lose message. You can probably get a higher throughput and lower latency on the same hardware. Whether message loss is acceptable depends on very much on the application. For example, with sensor reading the metrics that are transmitted periodically on an occasional missing data point is perhaps not important, since an updated value will be sent to a short time later. However, be aware that if a large number of messages are dropped and it may not be immediately apparent in the metrics, then apparent that the metrics are incorrect. Beware that if a large number of messages are dropped, it may not be immediately apparent that the metrics are incorrect. If you are counting events, it is more important that they are delivered reliably, since a lot of message means incorrect converts. Since every lost messages means incorrect converts. A nice property of batch processing system we explored in chapter 10 is that they provide a strong reliability guarantee. Failed tasks are automatically retried, and partial output from failed task is automatically discarded. This means that the output is same as if no failures had occurred, which helps carry this means the output is the same as if no failures had occurred, which helps simply the programming model. Later in this chapter, we'll examine how we can provide similar guarantees in the streaming context. A number of messaging systems use direct network communication between producers and consumers without going via intermediary nodes. A number of messaging systems use direct communication between producer and consumer without going via intermediary intermediate intermediary nodes. UDP multicast is widely used in financial industries for streams such as stock market fields where low latency is important. Although UDP itself is unreliable, application level protocols can recover most lost packets. The producer must remember the packet it has sent so that it can retransmit them on demand. Brokerless messaging systems such as ZeroMQ and Nana MSG take a similar approach in implementing publishing of subscriber messages over TCP or IP multicast. StatsD or Burbic also use unreliable UDP messaging for collecting metrics from all machines on the network and monitoring them. In the StatsD protocol, counter metrics are only correct if all messages are received. Using UDP makes the metrics at best. If the consumer exposes a service on the network, producers can make a direct HTTP or RPC request uh, to push message to the consumer. This is the idea behind webhooks, a pattern in which callback URL of one service is registered with another service and makes the request to that URL when an event occurs. Although this direct system, direct messaging system works well in the situation where they generally require application code to be aware of the possibility of message loss. The faults they can tolerate are quite limited, even if the protocols detect and retransmit the packets that are lost in the data. They generally assume that producers and consumers are constantly online. If a protocol, if a consumer is offline, it may miss messages that were sent while it is unreachable. Some protocols allow the producer to retry failed message delivers, but this approach may break down if the producer crashes, losing the buffer message that it was supposed to retry. A widely used alternative is to send messages via message broker, also known as messaging queue, which is essentially a kind of database that is optimized for handling message streams. It runs as a server with producers and consumers connecting it to it as a client. As clients, producers write message to the broker and consumer receive them by reading from the broker. By centralizing the data in the broker, the systems can more easily tolerate clients that come and go, connect, disconnect, and crash, and the questions of durability is moved to the broker instead. Some message brokers only keep messages in memory, while other, depending on configuration, write them to disk so that they are not lost in case of broker crash. Faced with slow consumers, they generally allow unbounded delays as opposed to dropping messages for back pressure, although this choice may also depend on configuration. A consequence of queuing is also that consumers are generally asynchronous. When a producer sends a message, it normally only waits for a broker to confirm that it has buffed the message and does not wait for the wait for the message to be produced by consumers. Correct. A consequence of queuing is also that consumers are generally asynchronous. So when a producer sends a message, it normally only waits for the broker to confirm it that it has buffered the message and does not wait for the message to be processed by consumer. So this delivery to consumer will happen some after at some undetermined future in time, often with a fraction of a second, but sometimes significantly later if there is a queue backlog. Our message brokers compared to databases. Some message brokers can even participate in two-phase commit protocols using XA or JTA to PC. This feature make them quite similar to nature to database, although there are still important practical differences between message brokers and database. Some message brokers can even participate in two basic protocols using XA or JTA. This feature makes them quite similar in nature to databases, although there are still important practical difference between message brokers and database. Database usually keep data until it is explicitly deleted, whereas most message brokers automatically delete messages when it has been successfully delivered to its consumers. Such message brokers are not suitable for long-term data. Such message brokers are not suitable for long-term data storage. Since they quickly delete messages, most message brokers assume that their working set is fairly small, that is, the queue is short. If broker needs to buffer a lot of messages because of the consumer are slow, perhaps spilling messages to disk if they are no longer fit in memory. Each individual message takes longer to process and the overall throughput may degrade. Okay, if the broker needs to buffer a lot of messages because the consumer is slow, each individual message takes longer to process and the overall throughput may degrade. Databases often support secondary indexes and various ways of searching for the data, while message brokers often support some way of subscribing to a subset of topics matching some pattern. The mechanisms are different. Both are essentially ways for a client to select the portion of data that it wants to know about. When querying a database, the result is typically based on a point-in-time snapshot of the data. If another client subsequently writes something to the database, that changes the that changes the query result. The first line does not find out that its prior result is now outdated unless it repeats the query or polls for changes. By contrast, message brokers do not support arbitrary queries, but they do notify clients when the data changes. This is the traditional view of message brokers, which is encapsulated in standards like JMS, AMQP, and implemented in software like RabbitMQ, ActiveMQ, HornetQ, Cupid, TVCo, Enterprise Management, IBM MQ, Azure Service Bus, and Google Cloud Pub. When multiple consumers read messages in the same topic, two main patterns of messaging are used as illustrated. Load balancing. Each message is delivered to one of the consumers, so the consumers can share the work of processing message in the carrier. Each message is delivered to one of the consumers, so the consumer can share the work of processing the message in the topic. The broker may assign the messages to consumers arbitrarily. This pattern is useful because when the messages are expensive to process, and so you want to be able to add consumers to parallelize the processing. In AMQP, you can implement a load balancing system by having a multiple client consuming from same queue. And in JMS, it is called a shared subscription load balancing fan out. Each message is delivered to one consumer, so the consumer can share the work of processing message in the topic. The broker may assign messages to consumers arbitrarily. This pattern is useful when the messages are expensive to process, and so you want to be able to add consumers to parallelize the process. Fan out भनेको each message delivered to all of the consumers. Fan out allows several independent consumers to each tune into the same broadcast of message without affecting each other. The streaming equivalent of having several different batch jobs that read the same input file. This feature is provided by topic subscription in JMS and extends quality in AMP. The two patterns can be combined. For example, two separate groups of consumers may each subscribe to a topic such that each group collectively receives all the messages, each but within each group, only one of the nodes receives each message. Consumers may crash at any time, so it could happen that a broker delivers a message to a consumer. Consumers may crash at any time, so it could happen that a broker delivers a message to customer, but consumer never processes it or only partially processes it before crashing. In order to ensure that the message is not lost, message broker use acknowledgements. A client must explicitly tell the broker when it is finished the processing a message that a broker can remove it from the queue. If the connection up to the client is closed or timed out without the broker receiving acknowledgement, it assumes that the message was not processed. Therefore, it delivers the message again to another consumer. Note that it could happen that the message actually was fully processed, but the acknowledgement was lost in the network. Handling this case requires atomic commit protocol. Mm. When combined with load balancing, this redelivery behavior has an interesting effect on the ordering message. The consumer generally process messages in order they were sent by producers. However, consumer 2 crashes while processing message M3. Get it? The consumer generally process the message in order they were sent by the producer. M2, M3, M4. However, consumer 2 crashes while processing the message M3 at the same time consumer is processing the message M4. M2, M4, M3, M5. The unacknowledged message M3 is subsequently re-delivered to consumer 1 within the with the result that consumer 1 process message in the order M4, M3, M5. Thus, M3 and M4 are not delivered in the same order as they were sent by producer 1. Even if the message broker otherwise tries to preserve the order of message as required by both JMs and APK, the combination of load balancing with redelivery inevitably leads to message being reordered. To avoid this issue, you can use a separate queue per consumer. That is, not use the load balancing feature. Messaging message reordering is not a problem if messages are completely independent of each other, but it can be important if there are several causal dependencies between messages and also that data. Sending a packet over a network or making a request to a network service is normally a transient operation that leaves no permanent trace. Although it is possible to record it permanently using a packet capture and logging, we normally don't think of it that way. Even if message brokers that durably write messages to disk and quickly delete them again after they have been delivered to consumers because they are built around the transient messaging mindset. Database and file system take the opposite approach. Everything that is written to a database or file is normally expected to be permanently recorded, at least until someone explicitly chose to delete it. This different in mindset has a big impact on how derived data is created. A key feature of batch process is that you can run them repeatedly, experimenting with processing steps without risk of damaging the input. This is not the case with Inaru. Message Receiving a message is destructive if the acknowledgement cause it to be deleted from the broker, so you cannot run the same consumer again and expect to get the result. If you add a new consumer to the messaging system, it typically only starts receiving the message sent after the time it was registered. Any prior message you are already gone and cannot be recovered. Contrast this with files and database, where you can add a new client at any time and can read the data arbitrarily far in the past as long as it has not been explicitly overwritten or deleted by the application. Why can we not have a hybrid combining these durable storage approaches of database with low latency notification facilities of messaging? The idea is behind the log-based message brokers. A log is simply an append on the sequence of record on disk. We previously discussed logs in the context of log structured storage engines and write-ahead logs in chapter. The same structure can be used to implement a message broker. A producer sends a message by appending it to the end of a log, and a consumer receives the message by reading the log sequentially. If the consumer reached at the end of the log, it waits for the notification that a new message has been appended. Unix tool tailf, which watches the file for data being appended, essentially works like this. In order to scale to a higher throughput than a single disk can offer, the log can be partitioned. Different partitions can then be hosted on different machines, making each partition separate log that can be read and written independently from other partitions. A topic can then be defined as a group of partitions that all carry messages of same type. This approach is illustrated in figure 11 when within each partition, broker assigns a monotonically increasing sequence of number or offset to every messages. The number of boxes are messaging offsets. Such a sequence of number makes sense because the partitions is append only, so the messages within the partition are totally ordered. There is no ordering guarantee across different partitions. Apache Kafka Kinesis streams and tutorial distributed log are log-based message broker that work like this. It's actually similar, but expresses YAML style API rather than log abstraction. Even though these message brokers write all messages to disk, they are able to achieve throughput of millions of messages per second by partitioning across multiple machines and alternatives by replicating messages. The log-based approach trivially supports fan-out messaging because several consumers can independently read the log without affecting each other. The reading a message does not delete it from the log. To achieve load balancing across a group of consumers, instead of assigning individual messages to consumers client, the broker can assign interpartitions to node. The log mesh approach really supports final processing because several consumers can independently read the log without affecting each other. Reading a message does not delete it from the log. To achieve load balancing across a group of consumers. Instead of assigning individual message to a consumer client, the broker can assign interpartitions to node in the consumer group. Each client then consumes all the message in the partition and it has been assigned. Typically, typically when a consumer has been assigned a log partition, it reads the message in partition sequentially in a straightforward single-threaded manner. The core screen load balancing approach has some downsides. The number of nodes sharing the network of consumer topic can be most the number of log partitions in the topic because messages within the same partitions are delivered to the same node. If a message is slow to process, it holds up the process of subsequent messages in that partitions, a form of it offline blocking. Thus, in situations where messages may be expensive to process, you want to parallelize processing on a message by message basis, and where message ordering is not so important. On the other hand, if the situation I compare to where okay, sorry, consuming a partition sequentially makes it easy to tell which messages have been processed. All messages within offset less than a consumer's current consuming a partition sequentially makes it easy to tell which messages have been processed. All messages with an offset less than consumer's current offset have already been processed, and all messages with a greater offset have not yet been seen. Thus, the broker does not need track of acknowledgements for every single message. It only needs to periodically record the consumer offset. The reducing bookkeeping overhead and the opportunity of batching and pipelining. This approach increase the throughput of log-based systems. This offset, in fact, is very similar to the log sequence number that is commonly found in single data database application, which we discussed in setting up new follower. In database application, the log sequence number allows a follower to reconnect with the leader after it has been disconnected and resume replication without skipping any writes. Exactly the same principle is used here. The message broker behave like a related database in the consumer like a follower. If a consumer node fails, another node in the consumer group is assigned the failed consumer partitions and it starts consuming the message at the last record offset. If the consumer had processed subsequent message but not yet recorded their offset, those messages will be processed a second time upon restart. We will discuss this way of dealing with the data in the chapter. Disk space usage. If you only ever append to the log, you will eventually run out of disk space. To reclaim the disk space, the log is actually divided into segments, and from time to time, all segments are deleted or moved to archive storage. We will discuss more sophisticated way of filling disk space here. If you only append to a log, you will eventually run out of disk space. To reclaim the disk space, the log is actually divided into segments, and from time to time all segments are deleted or moved to archive. Uh, this means that means if a slow consumer cannot keep up with the rate of messages, it falls so far behind that its consumer offset points to a deleted segment. It will miss some messages. Effectively, the log implements a bounded size buffer that discards all messages when it gets full, also known as a circular buffer or ring buffer. However, since that buffer is on disk, it can be quite large. Let's do a back of the envelope calculation. At the time of writing, a typical large hard drive has a capacity of 6 TB and a sequential write throughput of 150 MB per second. If you write, if you are writing a message at the fastest possible rate, it takes about 11 hours to fill the drive. Thus, the disk can buffer 11 hours worth of messages, after which it will start overwriting the old messages. This ratio remains the same if you use many hard drives in machines. In practical deployments, rarely use the full write bandwidth of the disk, so the log can typically keep buffer of several days or even weeks worth of message. Regardless of how long you can retain message, the throughput of a log remains more or less constant. since every message is written to disk anyway. This behavior is less contrast to messaging systems that keep messages in memory by default and only write them to disk if queue grows too large. Such systems are fast when queues are short and become much slower when they start writing to a disk. So the throughput depends on the amount of history retained. When consumers cannot keep up with producers. At the beginning of message systems, we discuss three choices of what to do if a consumer cannot keep up with the data with the producer sending messages, dropping messages, buffering, or applying bad process. In this taxonomy, the log-based approach is a form of buffering with a large but fixed buffer size limitation by the availability space. If a consumer falls so far behind the message it requires older than what it written on disk, it will not be able to read those messages, so the broker effectively drops the old message and that goes further back the size of the buffer can accommodate. You can monitor how far a consumer is behind the head of the log, raise an alert if it falls behind significantly. As the buffer is large, there is enough time for human operator to fix the slow consumer and allow it to catch up before it starts missing messages. Even if a consumer does fall too far behind and starts missing messages, only that consumer is affected. It does not disrupt any other service or other consumers. The fact is a big operational advantage. You can experimentally consume a production log for development, testing, or debugging purposes without having to worry about disrupting the production services. When a consumer shutdowns or crashes, it stops consuming resources. The only thing that remains is its consumer offset. This behavior also contrasts with the traditional message brokers where you need to carefully delete any queues whose consumers have been shut down. Otherwise, they continue unnecessarily accumulating messages and taking away the memory from consumers that are still active. We have drawn some comparison between message broker and database. Even though they have traditionally been considered separate categories of tools, we saw log-based message system brokers have been successful in taking ideas from China. That's it. Message brokers and databases. Even though they have traditionally been considered separate categories of tools, we saw that log-based message brokers have been successful in taking ideas from databases and applying them to messaging. We also go in reverse, taking idea from messaging systems and streams and applying them to this database. We said previously that an event is a record of something that happened at some point in time. The thing is that the thing that happened may be a user action or a sensor reading, but it may also be a write to a database. The fact that something was written to a database is an other. जाँदिनँ अनि कहाँ गएर आउँछु भन्नुहुन्छ नि त्यो त म एक्लै जान्छु होला गयो भने फिक्स छैन अलमोस्ट नट फिक्स जाँदिनँ नि होला दरबारमा त्यहाँ एउटा त्यो ऊ छ के भन्छ रेस्टुरेन्ट छ त्यहाँनिर होइन साँच्चै छैन छैन
फिक्स किन भन्नु न पछि भनौँला ए बिना पैसा र होइन होइन त्यही त बर्थडे सकिनु बाहिर एउटाको फेरि अर्को बर्थडे भन्नु न त पछि भनौँला अब त मलाई फुल जसो भन्नु न जान्न नि यहाँ पढिसक्नु पर्ने अहिले मात्रै भन्छु म आज सकाउनु पर्ने एकचोटि भनेर त सकाउँदा किन भनिदिनु न एकचोटि लास्ट एकचोटि अफिस छ नि त अनि अफिस त बेलुका सकिहाल्छ अनि 6 बजे सकिन्छ भने त म त्यही अनुसार भोलिको त्यो स्केड्युल मिलाउँछु नि त खाजा खाने खाना खाने होइन होइन म जाँदिनँ गएँ भने नि म आइहाल्छु के भयो कहिले आउने तिनीहरू त बिहानै आउँछ पेपर साइन गरेँ
We said previously that an event is a record of something that happened or in point of time. The thing is that happened may be a user typing or search query or a sensor reading, but it may also be a write to a database. The fact that something was written to a database is an event that can be gathered, stored, and processed. This observation suggests that the connection between database and streams are deeper than just the physical storage of log on disk. It is quite fundamental. In fact, a replication log is a stream of database write events produced by the leader as it processes transactions. The follower apply that the stream of writes to their own copy. In fact, a replication log is a stream of database write events produced by the leader as it processes transactions. The follower apply that stream of writes to their own copy of database. In fact, a replication log is a stream of database write produced by a leader as it processes transactions. The follower apply the stream of writes to their own copy of database and thus end up with the accurate copy and same data. The event in the replication log describes the data changes that occur. We also came across some state of machine replication principle, total order broadcast, which states that if every event represents a write to the database and every replica processes the same event in the same order, the replica will also end up in the final state. Processing an event is assumed to be deterministic operation. It is just another case of event streams. In this section, we will keep first look at a problem that arises in heterogeneous data system and then explore how we can solve it by bringing ideas from event stream to databases. As we have seen throughout this book, there's no single system that can satisfy all data storage, querying, and processing. In practice, most non-trivial application needs to combine several different technologies in order to satisfy their requirements. For example, using an OLTP database to serve user request, a cache to speed up command request, a full text index to handle search queries, a data warehouse for analytics. Each of this has own copy of the data stored in their own representation that is optimized for its own purpose. As the same or related data appears in several different places, they need to be kept in a sync with one another. If an item is updated in the database, it also needs to be updated in the cache, search indexes, and data warehouses. With data warehouse, this synchronization is usually performed by ETL processes by taking a full copy of database, transforming it, and bulk loading it into data warehouse. In other words, batch process. Similarly, we saw the output of batch, how in search indexes and data systems on the data might be created using batch processing. If a full if if periodic full database dumps are too slow, in that an alternative that is sometimes used is dual writes, in which the application code explicitly writes to each of the systems. If periodic full database dumps are too slow, if periodic full database dumps are too slow, an alternative that is sometimes used. If periodic full database dumps are too slow, an alternative that is sometimes used is dual writes, in which an application code explicitly writes to each of the systems. If periodic full database dumps are too slow, an alternative that is sometimes used is dual writes, in which the application code explicitly writes to each of the systems when data changes. For example, first writing to the database, then updating search index. If periodic full database terms are too slow, an alternative that is sometimes used is dual writes, in which application code explicitly writes to each of the systems when data changes. For example, first writing to the database, then updating the search index, then invalidating the cache entries, or even performing those writes concurrently. However, dual writes have some serious problems, one of which is a race condition illustrated in figure 2. In this example, two clients concurrently want to update item X. Client 1 wants to set the value to A and client 2 wants to set it to B. Both clients first write the new value to the database. Both clients first write the new value to the database, then write it to the search index. Due to unlucky timing, the requests are interleaved. The database first sees the write from client 1 setting it to value A, then the write from client 2 setting it to value B. So the final value in the database is B. The search index first sees the write from client 2, then client A, so the final value in the search index is A. The two systems are now permanently consistent with each other even though no error occurred. Unless you have some additional concurrency detection mechanism, such as the version vectors we discussed in the, you will not even notice that concurrent writes occurred. One value will simply silently overwrite another value. Another problem with dual writes is that one of the write may fail while another may succeed. This is the fault tolerance problem rather than concurrency problem. But it also has effect of two systems becoming inconsistent with each other, ensuring that they either both succeed or both fail in the case of the atomic two-phase atomic comic problem, which is expensive. If you only had replicated the database with a single leader, then the leader determines the order of write. So the state of machine replication approach works similar replicas of the database. However, there isn't a single leader. The database may have a leader and the search index may have a leader, but neither follows the other. So conflicts can occur. The situation would be better if there really was one leader, for example, the database, and if we could make the search index a follower of the database. But is this possible in practice? Since data gaps are the problem with most database replication log is that they have long been considered to be an internal implementation of detail of the database, not public API. Clients are supposed to query the database through a data model in query language, not the parse the replication log and trying to extract the data from them. For decades, many databases simply did not have documented the way of getting log of changes returned to them. For this reason, it was difficult to take any changes made in the database and replicate them used to a different storage technology such as search index, cache, or a data warehouse. More recently, there have been growing interest in change data capture (CDC), which is the process of observing all data changes returned to a database, extracting them in a form which they can be replicated to other systems. CDC is especially interesting if changes are made available as a stream immediately as they are written. For example, you can capture the changes in a database, continually apply the same changes to a search index. If the log change is applied in the same order, you can expect the data in the search index to match the data in the database. The search index is any the search index and any other derived data systems are just consumers in the change stream. Is it client one set x equal to client to the log of data capture append cursor and container applies to data. Mm, We can call the log consumer derived data systems. Is discussed in the introduction part. The data stored in the search index in data warehouse is just another view onto the data. The data stored in the search index in the data warehouse is just another view onto the data in the system of record. We can call the log consumers derived data system as discussed in the introduction to part 3. The data stored in search index and the data warehouse is just another view onto the data in system of record. Change data capture is a mechanism for ensuring data capture is a mechanism for ensuring that all changes made to the system of record are reflected in the derived data systems. So the derived systems have an accurate copy of the data. Essentially, change data capture makes one database the leader and turns the other into followers. A log-based message broker is well suited for transporting the changes from the source of database since it prevents the ordering of database. Database triggers can be used to implement change and data capture by registering the triggers that observe all changes to a data tables and corresponding entries to a change log table. However, they tend to be fragile and have significant performance overheads. Parsing the replication log can be a more robust approach, although it also comes with challenges such as handling schema changes. LinkedIn Dataverse, Facebook's Wormhole, and Yahoo's Serpa use this idea at a large scale. Bottled water implements CDC for bottled water implements CDC for PostgreSQL using an API that decodes write ahead log. Maxwell and do something similar, but MySQL person will be log mono Mongo River reads the MongoDB and records similar to Oracle. Like message brokers, change data capture is usually asynchronous. The system records the data, does not wait for the change to be applied in the converse before committing it. This design has the operational advantage, but adding a slow consumer does not affect the system of record too much, but it has downside that all the issues of replication lag may apply. If you have the log of all changes that were ever made to a database, you can reconstruct entire state of database replaying the log. However, in many cases, keeping all the changes forever would require too much disk space, and replaying it would take long. So the log needs to be truncated. Building a new full text index, for example, requires a full copy of the entire database. It is not sufficient to only open the log of recent changes, since it would be missing items that were not recently updated. Thus, if you don't have entire log history, you need to start with a consistent snapshot as previously discussed. The snapshot of the database must correspond to our known positions or offset in the change log so that you know at which point to start applying the changes after the snapshot has been processed. Some CDC tools integrate this snapshot facility while others leave it as manual operation. If you can only keep a limited amount of log history, you need to go through the snapshot process every time you want to add a new derived data systems. However, log compaction provides a good alternative. We discussed log compaction previously in as index in the context of log structured storage engines. The principle is simple. The storage engine periodically looks for logs record with same key, throws any duplicates, and keep the most recent logs update for each key. This compaction and merging process runs in background. Log structured log structure storage engines and updated with a special null value or tombstone indicating that the key was deleted and causes it to be removed during log compaction. But as long as the key is not overwritten or deleted, it stays in the log forever. The disk space required for such a compacted log depends only on the concurrent contents of the database, not the number of writes that have been ever occurred in the database. If the same key is frequently overwritten, previous values will be eventually be garbage collected, and only the latest value will be retained. The same idea works in the context of log-based message brokers and change data capture. If CDC system is set up such that every change has a primary key and every update for a key is a previous value for that key, then it's sufficient to keep the just for a most written right of the particular key. Now, whenever you want to rebuild a derived data system such as search index, you can start a new consumer from offset 0 of the log compact topic and sequentially scan all over all messages in the log. The log is guaranteed to contain the most recent value for each key in the database and may some be older values. In other words, you can use it to obtain a full copy of database contents without having to take another snapshot of the CDC source database. This log compaction feature is supported by Apache Kafka, as we shall see later in this chapter, that allows the message broker to be used for durable storage, not just for transient messaging. Increasing databases are beginning to support change streams as first-class interface rather than the typical retrofitted and reverse engineered CDC force. For example, RethinkDB allows queries to subscribe to notifications when the result of a query change. Firebase and CosDB provide data synchronization based on changed feed that is also made available to applications and Meteor users. The MongoDB upload to subscribe to data changes and update the user database. WorldDB allows transactions to continuously export data from databases in the form of stream. The database represents an output stream in the relational data model as a table into which transaction can insert tuples but which cannot be queried. The system then consists the log of tuples that committed transactions have been returned to a special table in the order they were committed. External consumers can asynchronously consume this log and use it to update their data systems. Kafka Connect is an effort to integrate change data capture to tools for wide range of database systems to Kafka. Once the stream of change events is in Kafka, it can be used to update derived data systems such as search indexes and also feed into stream processing system as described in the chapter. There are some parallels between ideas. The ideas we've discussed here, and event sourcing is the technique that was developed in the domain-driven design. There are some parallels between the idea we've discussed here and event sourcing technique. We'll discuss the event sourcing briefly because it incorporates some useful and relevant idea for streaming systems. Similarly, to change data captures, event sourcing involves storing the changes to application state as long as a log of change events. The biggest difference is that event sourcing applies the data at a different level of abstraction. In changes in change data capture, the application uses the database in a mutable way, updating and detecting records at will. The log of changes is extracted from the database at low level, which ensures that the database of write extracted from the database matches the order in which they were actually written, avoiding the race conditions. The application writing to the database does not be aware. The application writing to the database does not need to be aware that CDC is occurring. In event sourcing, the application logic is explicitly built on the basis of immutable events that are written to an event log. In this case, the event is stored in an append only, and updates or deletes are discouraged or prohibited. Events are designed to reflect things that happen at application level rather than low level state changes. Event sourcing is a powerful technique for data modeling. From an application point of view, it is more meaningful to record the user's actions as immutable events rather than recording the effect of those actions on a mutable dataset. Event sourcing makes it easier to evolve application over time, helps with debugging by making it easier to understand after the fact why something happened, and guards against application bugs. For example, storing the event of student cancel their course environment clearly express the intent of single action in a neutral fashion, whereas the side effects only one reward was added to the student impaired a lot of assumptions about the way data was later going to be used. If a new application figure is introduced, for example, the place is offered to a next person on the waiting list. The event sourcing approach allows the new site to be changed for the existing event. Event sourcing is similar to the chronicle data model, and there are also similarities between an event log and the fact table that you find in star schema. Specialized databases such as event store have been developed to support applications using event sourcing. Specialized databases such as Event Store have been developed to support applications using event sourcing, but in general, the approach is independent of any particular tool. Conventional database or a log-based message broker can also be used to build applications in this style. An event log by itself is not very useful because users generally expect to see the current state of systems, not the history of modifications. For example, on a shopping website, user expect to be able to see the current content of the cart, not append only list of all the changes they have ever made to the cart. Thus, applications that use sourcing need to take the log of events represented of the data in the system and transform it into application state that is suitable for data for showing to a user. The way in which data is read from the system. This transformation can use arbitrary logic, but it should be deterministic so that you can run it again, derive the same application state from the event log. Like with change data capture, replaying the event log allows you to reconstruct the current states of the system. However, log compaction needs to be handled differently. A CDC event for the update of record typically contains the entire new version of the record. So the current value for a primary key is entirely determined by the most recent event for the primary key, and log compaction can discard previous events for the same key. On the other hand, with event sourcing, events are modeled at a higher level. On the other hand, with event sourcing, events are modeled at a higher level. An event typically expresses the intent of user action, not the mechanics of state of update that occurred as a result of the action. In this case, later events typically do not override prior events, and so you need the full history of events to reconstruct the final state. Log compaction is not possible in the same way. Applications that use event source typically have some mechanism for storing snapshot of the current state that is delivered from the log of the trip, so they don't need to repeatedly reprocess the full log. However, this is only performance optimization to speed up the reads and recovery from caches. The intention is that the system is able to store all raw events forever and reprocess the full event of the log whenever required. We discussed this. The event sourcing philosophy is careful to distinguish between events and commands. The event sourcing philosophy is careful to distinguish between events and commands. When a request from a user first arrives, it is initially a command. At this point, it may still fail, for example, because of some integrity condition is violated. The application must first validate that it can execute the command. If the validation is successful and the command is accepted, it becomes an event which is durable and immutable. For example, if a user tries to Even is capable of distinguishing events, commands, when the request from a user first arrives, it is initially a command. At this point, it may still fail, or for example, because of some violated. For example, if a user tries to register a particular username or reserve a seat on an airplane for a theater, when the application needs to check out the username or a seat, When the check has succeeded, the application can generate an event to indicate the particular username was registered by a particular user ID or the particular sheet has been reserved for a particular customer. At this point, when the event is generated, it becomes a fact. Even if the customer later decides to change or cancel the reservation, the fact remains true that they formerly held a reservation for a particular seat, and change reconciliation is a separate event that is added later. A consumer of the event stream is not allowed to reject an event. By the time the consumer sees the event, it is already an immutable part of log. It may have already been seen by other consumers. Thus, any validation of commands need to happen synchronously before it becomes an event. For example, by using a serializable transaction that automatically validates the command and publishes the event. Alternatively, the user request to reserve a seat can be split into two events. First, tentative reservation, and then a separate confirmation event once the reservation has been validated and discussed in implementing linear storyline. This split allows the validation to take place in a synchronous process. Missions are in that batch process benefits from MTV when input file so you can run experimental processing of how does this fit with immutability?